Greetings, welcome back to my series on the Racket programming language. Today we're going to go through an example that you can find in the Structure and Interpretations of Computer Programs 2nd edition textbook. It's about how to do Huffman encoding, which is a way of compressing files. That's kind of the basis of all the major compression algorithms, actually. And it's an example of, again, how you can use trees in a slightly different way as a data structure to do the work here. And the main trick here is that if you're fairly clever about how you define this and you use this tree along with the set, that it's actually a fairly simple process to make this Huffman encoding. So first of all, what they've done here is that we have here all in a Huffman encoding, all the leaves of the tree are going to have a symbol and a weight. And the symbol, they use symbols here. This could be a character. And so basically the way they do this is they make a list and they have a tag here that says this is a leaf and it's a symbol and here's its weight. That tag is interesting in the fact that you could do a test that just says, hey, does this have any left or right branches? But this is actually just a simple way to make sure that you can go off and do this, because you can do this quick test here whenever you're given this whatever list is. You can say, is this a leaf, if it just is tagged as so. And then they have a couple of helpers here to get the symbol and the weight out of this tree. Now the weight is something that's kind of important, which is basically what this starts out is that you go off and examine a file and determine how many characters are in it. And the leaves start out with that weight. And then as you sum them up, you build up branches where each one of the nodes has the summed up of those weights. Okay, so here we go off and we have this for the symbols for the tree. Basically, if it's a leaf, we have to make a list out of the symbols. Otherwise, there should just be a list of symbols in that already. We should have the weight. Same thing here. It's the leaf and the weight of the leaf. Otherwise, it's in this tree part here. Now, the interesting thing about this is, well, the reason they're doing this slightly differently is that if you look here at the make leaf, it's just a list with the leaf, the symbol, and weight. There's no empty place for left and right. However, if you wanted to make a tree, the tree is a list that has a left and a right, and then a list of symbols and then a weight. So these are the slightly different. These differ if you're at a leaf or you're in basically a non-leaf part of the tree. So what they first have done here is that they make a code tree left and right, which is starting out the left branch and the right branch, putting this list here. Very simple. Now, the next thing that they've done is they define this thing called an adjoin set, which takes in a value x in a set. If that set is null, it goes ahead and just returns that list with a list of just that object in it. And basically what we've done here is that we go off and we check the weight of that node that we're adding. And if it's less than what's at the first part of this set, then what we return is the cons with that value in front of the rest of the set. Otherwise, we just take cons in and then do the rest, recursing on this thing. And what this adjoin set is really a ordered set of leaves. And that's what it's used for. So this is what maintains this ordering. So as soon as this is true, then it'll put this in. So basically, you can see that this maintains ordering for the set. Now what it goes off and does, we have a make leaf set here. It takes in a set of pairs, and what the pairs will be, in this case, it should be a character and a weight or a count that appears. And so we go off and do the standard set chat here. If null, pairs return the list. Otherwise, we create a pair. We get the first part of this pairs out of this. Create an adjoin set by making a leaf that has a value here and making the leaf set for the rest of the pairs. So this set this up. And now we're going to get into the decode and encode parts. First of all, we're going to do the decode. This is a helper program for decoding, which it says choose a branch given a bit and a branch, and basically a bit's going to be 0 or 1. We're just going to use numbers here. So if it's equal to 0, you go to the left. If it's equal to 1, you go to the right. Otherwise, it's bad. So decoding the bits given this tree that we're going to build, there's a helper function that they've made, and they use a slightly different notation than I use. There's a code -1 for the parts here, but it's the same type of embedded function that you would expect that just takes the bits in the current branch. If we're null, we return this, just give it an empty list. Otherwise, we let the next branch, we choose which branch we do based on the first bit. And if we're at a leaf, then what we do is we go ahead and cons up basically a list of the symbol from the next branch and then decode the rest of the bits. So that should pick out the character that we're at and then decode the rest of the message. Otherwise, if it's not a leaf, then we just go off and do the decode for the next part of the branch. And then we just basically call this recursively. Makes this initial call to this part with the initial part of the bits in the tree. So this is just your standard kind of recursive helper. And for encoding the symbol in a tree, we have a recursive helper here. Again, for the leaf. And what we're doing here is that what happens is that if we're at a leaf, we should have it so that the symbol that we're trying to encode or character is in that tree. If it's not, if it is, then we just return the bits we've accumulated so far. Otherwise, we say, hey, this is an error. We have a bad symbol here. Otherwise, we capture the symbols on the left and the right part of the tree. And what will happen is that we would determine what part of the tree to go down, the left or the right, whether or not the symbol is in the left symbols or the right symbols. And you can see that here as we just make a recursive call to the left or right branch. And if we go to the left, we append 0 to the bits. And if we go to the right, we append 1 to the bit list. Now, if we don't see the symbol in either left or right, then we have a bad symbol. We have a symbol we don't know how to encode. And then this is a basic helper at the very top, which is at the very top of the tree. The tree will contain a list of all the symbols it can encode. And so if that symbol isn't in that top of the tree, then this tree is bad. And so this doesn't even make sense. So what we're going to have is a bad symbol at the, and we're at the root there of the tree. So what we can do is to encode a message in a tree. Basically what it does is it goes off and says, okay, checks to see if the message is null and returns an empty list, and it appends together. This is the bits for the first part of the message, and then cons that with the list for the rest of the message. So, and then this is the fascinating part. To make this tree from the set of leaves that we have, which is basically made up from that pair, it's fairly simple. If we have only one leaf left, we just return that leaf. Otherwise, call this successive merge on the adjoint set of making a code tree from the two parts that we have left, the first two leaves we have, with the rest of the leaves. And you just keep doing this over and over and over again until it's merged all the way up so that we only have one thing. And if you think about how this works, this literally is going to take these things and build up this set and build up this tree so that every single branch eventually goes up and then all the symbols are encoded. The thing that's really interesting about this is that if you look at the iterative version for this algorithm, it actually, the most efficient version of it uses a specialized data structure that kind of combines a tree and a list. You literally have things where it has 3 pointers. It has a left and right and then a next pointer. And you take this list and then you kind of transform it into a tree using this very iterative process. It's a fairly complex iterative algorithm. However, if you use this recursive notion, using the successive merge idea, we're building this adjoint set. This is actually very effective. It may be a little bit slower, but it's way simpler to understand. And all you have to do to make a Huffman tree is to take that pair, that list that we've talked about, and just run that successive merge on the leaf set of pairs. So again, feel free to take a lot of time and review this. But what we've done here is we have now successfully made a Huffman tree. And I'm going to treat this as a module, and I'm going to go ahead and provide these basic, I'm going to expose these basic parts so we can decode and encode and generate an initial tree. Okay. And now I'm going off and I'm going to show this in an example here. And I'm going to run this. Here. So what I've done first here is I'm going to first of all, the thing that we need, obviously, before we can start this whole process is that pair list, the symbols, and then how often they appear in the message. And so what I'm doing here is I'm taking in a file that I got online, and I'm going to try to build this up by reading through that file one character at a time. And what I've done here is that I am now using a hash table to track how many times a character appears. And so that's what I've done here, is that we have this character hash, which is calls this built-in function in Racket called makeHash, which basically makes a hash table. It also defines a port, which is a port to read text from this file path here above. Now I define this helper function that doesn't take in any arguments because it really doesn't need to, as you'll see. And the reason being is that the loop condition isn't dependent on what argument is being passed to it, some argument going to a certain limit. It ends when we have nothing to read from the file. So what we do is we constantly read in a character from that file port, and if what's returned from read character is an end, what's called an EF object, then we return the hash that we've built up already up here. Otherwise, we do things. And this is the first time we're going to actually use something that looks like an imperative programming and do something that looks like an assignment. So this is what happens. I'm going to first look and see if this hash has the key already. Does this character already live in the hash table? All right. If it does, I'm going to call this function hash-update bang. And this exclamation point, or the bang at the very end of it, is very important. In Racket, there's a convention that anything that mutates something should have that exclamation point at the end. And what's happening here is that it is going to change this char hash in place. It's not going to make a new hash table with all those entries in it. What it's going to do is, in this case, it is going to take that, it's going to take the hash table, the key, and it's going to take a function. And what it'll do is it'll call this function on the value of that key value pair in the hash map and replace the value with that call this function. So in this case, what we're doing is we're literally just adding 1 to the value that's in that hash map. So, but if we don't have it there, then we're going to set it by changing the hash again, and we're going to do a hash set, and we're going to add that character as a key with a value of 1. And then we're going to recursively call ourselves again. And then what I need to do is that to get into a slightly better form, I'm going to take the hash, there's a built-in function called hash map, and I'm going to call this function on it, and, take the result of calling this function, which is a hash table map, and then it's going to split this out, and it's going to make a set of lists of the key value pairs. So let's see what that looks like here, but I can just go ahead and call, we define the frequency list here with that call. Sorry, my typing skills just seem to escape me today. All right, so let's run that. And over here, indeed, we have a huge set of things. So first of all, this is all the characters that are in this text file. This does not necessarily mean that every single character in the alphabet is in this text file. For example, the letter Z actually never comes up. There's a couple things that are in here, like new line characters, space characters. Not exactly where this one came up from, but there it is. So now what I'm going to do is now that I have that frequency list, which is basically, okay, these characters and the frequency that they appear in, I'm going to now call generate Huffman tree on that, and I'm going to define that as a sample tree, and so I can just print out the sample tree. Tree as follows. And you can see it makes a huge list here. It's pretty large, as you imagine. But it's gone through and it's basically made up these huge types of leaves. I can try to make it look a little bit better by pretty printing it and then stretching out the result. Yeah. So you can see here, like it becomes a pretty massive structure with these very leaves at the very end, and you can start to see how they're building up in the left and right branches. And it might be a good exercise to come up with something that's like a better visualizer to print these things out by coming up with a custom printer for doing this versus just looking at the underlying list as it is. Because obviously it's one of those things that's very confusing. But you can see here at the very, very top here, or the very, very end, we have this huge thing here, which is basically all the letters in the file. And this is the root, and then we have obviously the left and the right, and we can see how things split off from there. So we will move this back over. And I will come this out for now. And let's take a look at what encoding the poem against the tree looks like. Let's see, did they spell that? Oh, no, poem encoded, not contents. Oh, wait a minute. Sorry, I do have to let this in here because I actually have to load the file in because we want to load in. Not only do we need to load it in to make the frequency list, but in this case, I want to encode the contents of it. So what I've done here, I guess I should have explained this versus just brushing over it, is we have there's a special built-in function called port to list, which basically will take a function that you apply to each character that comes from this thing. And so what this will do is it's like very much like a map, but basically it just will make a list by applying each character that comes out of here, by applying this function to the port that is given in the last type of thing. So, and it'll do that until there's an end of file on that port. So in this case, what we're doing is we're going to read a character from that port. And so what this will return a list of individual characters. As you can see here, this massive, massive printout. Let's just see if this actually works a little bit better. I'm doing a pretty print again. Did not seem to help much in this regard. I'll just take this out so we're not. Yeah. So you can see it's actually returned a list of the basically every character in this poem, and then the poem encoded. Is obviously here we see it as a huge list of ones and zeros. So one of the things that's interesting about this is we can take a look and say, now that we have the poem contents here, I'm curious about, like, let's say, what is the length of poem contents, which is basically in this case, how many characters are in it? And I'm going to do the same. For a poem coded. Alrighty, let's take a look here. Poem contents 166.5. The number of bits in the encoded poem is 5,173. Now, at first it seems obviously, well, this is a huge waste. But actually, remember that this is bits. So what we should probably do here is it's a much more accurate representation to think about this as what we're really looking for is the length of poem encoded here divided by 8. That's a fair comparison. So, of course, in the scheme, way of doing that is obviously prefix. And we can run this again. And we can see that this is actually 646, and then, so basically 6480 bytes versus 1178 bytes. So there's actually a significant savings there. Now, that being said, in the actual file, if we wanted to do this, we'd obviously have to provide the tree as well. So let's take a look at the sample tree. See how many items are in it. So yeah, that's okay. So it actually would only have 4 things. So we need to have something that would count the nodes in it. So that might be a fun exercise. Now, in this case, I would imagine that if you added in the tree and then put in just the text here, you probably wouldn't get that great a compression. There are ways of actually collapsing the tree to make it a lot more compact in terms of encoding, and that's what things like zip and gzip and bzip and all and so on and forth, that's what they do. So it could be effective for even this small of a file. But you can see that basically we have indeed had some encoding here. And this is a fun exercise to just kind of go through. And the reason I go through it is I would encourage you to, again, go off and look at the iterative version of this algorithm and see that this one, while it's not completely obvious, it actually does fall out fairly simply from this very simple idea of successfully merging this list up in leaves. And not only that, but we are using, again, the fundamental list structure in Racket in a fairly effective way in terms of space. And one of the things that we're doing that we're taking advantage of is, in this case, that lists can have different items in them, and they could be different sizes, and that we're taking full advantage of that by the fact that the leaves only contain the area information that the leaf would need. We don't have any null pointers here for left and right. We only have left and right parts when we have basically something that is a branch in the tree. The second thing to point out is that, again, in this IO example, we have our first example of mutation, and hash sets are an obvious example of where you would need to mutate something. In Racket, remaking lists in a recursive way can be fairly fast. There's lots of ways that they control that in terms of memory. That's highly optimized. A hash table is something, though, that you definitely want to update. You do not want to make a new value in the hash table every time you add a key or update a value. That just becomes a completely too expensive an operation, even if you're using lists very efficiently underneath it. So this is where you have to use these types of mutating functions. And the interesting thing about this is that, why is Racket so, keen on pointing this out? And the reason being is there's a couple reasons. One is that this exclamation sign kind of notes that this basically may not return something, or may not have a return value that means anything. For example, in this hash set char hash C1, what makes sense here? Oh, if it really worked, it's true. Does it return false if it's already in there? It's not like a regular function that we expect to have a value that we could do something with. And so that's one reason. The other two is that they want to make sure that when you use mutation, that it really shows up, and to think about it. And because, like higher functional programming languages in general, mutation introduces a lot of complications. And in imperative programming languages, those complications are just there as just a fundamental part of it. And you really can't work around them unless you try to really reduce the surface language to something that would be like a reduced functional language in the first place. So, and where it comes down to is that in terms of reasoning about programs like this, when you introduce obviously things like mutation, things become a lot harder. And we're going to talk about that more in future episodes. But anyway, this is a fun little exercise on the Huffman encoding in trees. I will hopefully have my GitHub link up soon. So some of the files I've been going on and using in this video will be made available. And thanks for watching. Bye.